Somebody just got kicked out, but if they got kicked out, just come right back in. Everyone see my screen?
Yes.
Yeah, I can see it.
All right, okay, cool. So this is where we left off last time, right? We were talking about free body diagrams. So I can go backwards because it's been like a week, right? So the biggest concepts that we have is really trying to understand Newton's laws, right? So this is where we're starting at, right? And there's 3 different laws. First one, an object in motion stays in motion. Basically, object at rest will stay at rest, and the object in motion will stay in motion unless acted upon by unbalanced force. Second law, when forces are unbalanced, the net force is equal to the mass of the object times the acceleration of the object. Then we got the third law, for every action, there's an equal opposite reaction. Now, how do we even get to those laws? We talked about inertia, mass, but I want to start with us talking a little bit about force, right? So forces, again, a force is a push or a pull upon an object resulting from the object's interaction with another object. It's a vector quantity. We have different forces such as contact force, which is physical contact. We got at a distance forces, which is without physical contact. And then this one right here, right? Talking about free body diagrams. We use free body diagrams to represent the forces acting upon an object. And then the net force, when we talk about it, is the sum of all the individual forces acting on an object. Now, why did I want to focus on it? Oh, forces come in pairs too. I wanted to focus on all of that, right? We talked about different types of forces to bring us back here to get us to here, right? So now when we have a free body diagram, right, we want to actually label all the different types of forces that act on the object as it's in motion. So in this one right here, right, I'll kind of just go through this one and let it be seen. We have a sledder, right? It reaches the bottom of the hill, right? And he's close to right where I was slowing down. So if you can imagine, just picture a person that's sledding and they're going down at the hill, right? They get to the bottom of the hill, and once they get there, they just slide and slide and slide and slide and slide. Now, when they slide and they start to slow down, right? What causes them to slow down? What do you think causes somebody to slow down if they're sliding down a hill?
Friction.
Friction, right? We got some friction. Now, in this case, right? If it's a sled, is it what's the surface they're probably going on? Snow or maybe some ice or something like that, right? Now, would you consider that snow and ice have friction on it? Okay, we can go with that. It might be, I would kind of counter saying it's a little smooth, but only because when you look at the free body diagram, you'll see why. But when you're going down really fast and you're coasting, right? You do have friction, but what else is pushing against you? The air, right? Now, remember we said, how do we describe air resistance? From the wind, right? And that's similar to what? What type of force? If we just talked about it. Not normal force, but we just talked about it. Friction, right? But just with what? Air, right? So when we look at this free body diagram, right? That's what we have. 1 second. That should be good. You can still see my screen, right? All right, okay. So now we have this one. This is our free body diagram, right? Now, how many forces do we have in total? You said how many? 3 forces, right? Now, we want to say we had our 2 laws. Remember, we had our first law, which is Newton's law. Object in motion stays in motion. Now, what does that relate to? What type of forces? Remember, we talked about balance and unbalanced forces.
So unbalanced.
So if we have balanced forces, our net force should be equal to what? Our net force should be equal to 0. What does that mean that our net force is equal to 0? I probably did. Hold on.
It's at rest.
It's at rest. Or it's
Acceleration.
it's continuous motion. No acceleration. There we go.
Before we go any further, I had a question about F norm because the normal force kind of confuses me. Could you just explain what it is one more time?
Do you see my screen?
Mm-hmm.
There we go, right there. The different type of forces, right? So let's go over this real quick. We have weight, or the force of gravity, is the force at which the Earth, Moon, or other massively large objects attract one another towards itself, right? So that's like the force that helps us not only by our weight, but also pulls us together to we have like orbits and stuff with our planets, right? Then we have normal force. It's the force exerted by a surface as an object moves across it. I'll go through the whole thing. We have spring force, the force exerted by a spring when two objects are connected. Frictional force, force exerted by a surface as an object moves across it. Air resistance, the type of frictional force that acts upon us to travel through the air. What else we got? Tension, string, rope, wire, cable, and then applied force is applied force by a object, a force applied to an object by a person or another object. So those are all the main forces that we're going to see in here. So normal force usually comes when you have something that's on top of a surface that's supporting it, right? So when we think about that with this, right, what does that mean in this scenario of a slider, right? If I have a weight that's pulling me down through the force of gravity, right, but my normal force is counteracting that to where, look at those arrows. Are the arrows a different length or same length?
They're the same.
Same length, right? So that means my force of gravity has one amount of newtons, right? But then the normal force, how much do you think the normal force would be?
The exact same.
The same.
The exact same. So now, if those forces are exact same, are they balanced or unbalanced?
They're balanced.
They're balanced, right? So do we have an acceleration?
We do not.
No. So what does that mean in terms of the vertical? Am I accelerating up or accelerating down?
You're not moving.
Not moving. That's where object is still in motion. But what does that mean?
You don't have no velocity?
Now that I don't have any velocity, think about the actual, what am I doing? What's the actual scenario? And like what really was happening?
You're on a sled.
You're on a sled coming downhill. So if I was accelerating, what would I be doing?
Going faster.
In the vertical.
Laying down.
Think about it. If I was accelerating and up and down, right?
Oh, you would be sitting up.
Not sitting up, but if I was accelerating up and down. Gravity's pulling me down to the center of the earth. What if gravity was winning? Where would I go?
Down. On a
Down
sled.
into what?
Like a lay down position?
Not in a lay down position. I would go down into where?
The ground.
Into the ground, like actually into the ground. I would actually get pulled down into the ground. But if normal force was winning, let's just say some force was winning above, right? Beating gravity. What would happen? Think of Michael Jordan.
He would overpower it. So the normal force will overpower the gravity.
And then what would happen? We're getting there. If the normal force or whatever force is counteracting gravity, if I'm hold on, let me say it like this. If I'm defying gravity, what am I doing?
That's the dominant force.
You're jumping, you're in the air, you're moving.
Exactly.
Upwards.
I'm in the air. But that would be if my forces were what? Balanced or unbalanced?
Unbalanced.
In this sledding situation, is the normal force them jumping off a hill?
Hold on, wait, no. Hold on. You just said it right there, Victory. Unbalanced. That would be if it was unbalanced. But right now, we just said these forces are what?
Balance.
Balanced. So therefore, because
Mhm.
these forces are balanced, would I be in the air or on the surface?
You'd be connected to the surface.
So
And is
that's
the
what
normal force the force of you being on top of the ground?
the normal force is what supports me on the surface. Hold on, let me go back to definition.
So does that mean as long as the surfaces of two different objects are touching, or like there is a normal force and a force of gravity?
So then we have the force of gravity that pulls it down. Then we have the normal force, which is exerted by a surface as an object moves across it. In that sledding example, right? We're moving across the surface. What would it be? Either snow or ice. And we're connected to the snow or the ice. As we're connected to the snow or the ice and we're traveling, we don't leave the ground. So that means there has to be some force supporting us because we are actually being pulled by the force of gravity throughout the entire motion. Does that make sense?
Yes, it does make sense.
Could you say the last part? You said it will mean we will be what by gravity? Because the motion.
We are being pulled by a force of gravity the entire time because we all have a what?
A 9.8 gravity.
Yes, gravity, but like that turns into a force of gravity, which is also known as W word. Weight. We all have a weight. So we all have a weight that we feel, right? That weight to keep us on the surface has to be counteracted with a force. That force is the normal force. So now in the vertical, are our forces balanced or unbalanced?
They're balanced.
So with our forces being balanced in the vertical, right? We should be connected to the surface. But now we're moving, coasting rightward, but we're slowing down. Slowing down gives the indication of what? Deceleration.
Change in the
if
rate
we're
of
decelerating-
acceleration.
Go ahead. Yes.
I was going to say change in rate of acceleration. It's decreasing.
Not change in rate of acceleration, but change in velocity,
Velocity, I'm sorry.
which causes
Your rate
Change
at
in
which you are
not changing direction, but causes what type of constant
constant acceleration.
There we go. Change of velocity. Change of velocity over time equals acceleration. So now, because we're slowing down, we know we have some type of acceleration. We just said deceleration, but like we know acceleration is present. So if acceleration is present, let's back it up. If acceleration is present, does that mean my forces are balanced or unbalanced? Say it louder. Unbalanced. Good. And how can we tell our forces are unbalanced? Look at our free body diagram.
The length in a direction.
Now on the left, we see what?
Air.
Air resistance, right? Now, is there a force on the other side of it?
No,
No. So is it balanced or unbalanced?
it's unbalanced.
So think about it. If our motion was already coasting rightward and there's a force going to the what direction, left or right? To the left. So it's going against the motion of that object, right? So now we have acceleration against the motion of the object, which is going right. So now, because the air resistance is going left, is it going to speed up or is it going to slow down? Slow down. Good. So now with it slowing down, we know that we have unbalanced forces in the direction of the acceleration is opposite the direction of motion. So now we're going to see it slow down. This is why this free body diagram makes sense. So yeah, the acceleration, right? It would be meters per second squared. And then you would say, like, say if it was 20, right? But what you just said with the negative, what did you add? Yeah, what did you add? What does the negative represent really?
I'm going down the opposite direction.
Opposite direction. Direction. So the negative really tells us the direction. When you say negative, it's not really about positive or negative, it's about which way is it going. Because when you say negative, we know that it's moving to the right. So now negative acceleration means the acceleration is in the direction left, which means that it's going to actually start slowing down. Now, if it was positive, that means the acceleration is in the direction of the motion, which is right, which means it'd be speeding up. Positive or negative just tells us the direction, which is important for knowing which actual concept we're doing. Speeding up, slowing down. Now that I went over that whole entire problem to give you a kind of overview of what we've done so far. Talked about forces, and we talked about balanced and unbalanced forces, the types of forces, and then relating that to both the first and second law. The first law, if the forces are balanced, then the object in motion stays in motion until it's acted upon by unbalanced force. When it's unacted upon by unbalanced force, that moves us into the second law, that the sum of the net force is equal to mass times acceleration, which we see here. The top part, first two, in vertical, force is balanced, so we know the sum of the forces is equal to 0. So that means in real world application, we're traveling on a surface and we're staying connected to that surface. And then when we go to, yes, I did say, I don't know if I said that before. Yes, like normal force is the force that prevents you from falling through the earth. Yes. That's a good. And then you have the second part, which now we're looking in the horizontal left and right. We see that the forces are unbalanced because we have non-acceleration, right? So that unbalanced force causes us to accelerate, which means we're slowing down, which is still decelerating, which is accelerating. So now we have unbalanced forces left and right. So first law in the first half in the vertical, second law in the horizontal. So we covered a lot in just that one little problem, right? To be able to do problems like this, right? So that was conceptual. And I think I covered this last time, right? To where now we can actually start to use the concept of Newton's first law and second law to find actual mathematical quantities. Now, this is nothing new. It's not nothing crazy, but it's the same scenario that we just talked about conceptually, right? So one more time, let's go through it, right? So they gave us a free body diagram to work with. So I'm gonna redraw it up here. Once again, we have a slitter and we have 3 present forces. F norm, force due to gravity, and then I think this is friction. Right? And they all have different values. Norm is 600 newtons, and gravity is 600 newtons. And then we have friction, which is 100 newtons. And I gave you a little hint, right? I said the sum of the forces is equal to mass times acceleration. Well, let's think, right? First, if we look at our diagram, and you can look on the slides too, right? What do we notice about the length of the arrows in the vertical, F norm and F grav? You said that they're the same. So now what you look at them, they're the same, right? Look at the numbers, right? Are the numbers the same as well? So when we've seen these numbers are the same, the arrows are the same, can we assume that the forces have the same amount? So with assuming the forces have the same amount, will we consider them balanced or unbalanced? Balanced. So now, remember, let's correlate, right? When we're talking about balanced forces, the sum of the forces is equal to what? 0 when they're balanced. Now, what does that mean? That means, let's say, up. I really like to say it's the sum of the forces equals 0, but basically, what's up is equal to down, or what's left is equal to right. So I usually write it like this: up is equal to down. In this case, because we're talking about the vertical, right? Usually it could be like Fy, right? Vertical. So that means my F norm is equal to my F gravity, which we see, right? 600 equals 600, right? Now, why is that important? Let's stop right here. Let's move over to this part, right? How many forces do we have in our left, right? 1. Just 1 force, right? Is there something counteracting this? No. So it's just this 1 force on this side and nothing on this side. Will we consider this force balanced or unbalanced? So now it's unbalanced, right? So now that's unbalanced. The sum of our forces is equal to what? mass times acceleration. And I'll do this in the X for like left and right? So now we have in the X this way, the sum of our forces is mass times acceleration. And this way, the sum of the forces equals 0, right? Now, what's the sum of our forces in the X?
What did you say?
What's the sum of the forces in the left and right? Horizontal.
100.
What forces? Yes, it's 100. What forces are present?
I can't really. Oh, friction.
Right now, it's just friction, so it's just 100. It would still be yes, because it's just you're gonna know the direction is the opposite. Well, we could just leave it as 100 right now, right? So now we know whatever that sum of the forces is equal to the mass times acceleration. We know it's 100, right? But we want to figure out, what do we need to figure out? The sum of the forces, and actually, we just figured that out. We just figured out the sum of the forces. What is the sum of the forces? 100. Because the sum of the forces in the Y is what? 0. And then the sum of the forces over in the left and right is. So we know that the sum of the forces now for this part is 100, right? But we need to find the mass and acceleration. Now, why I keep going back and forth between the balance and unbalance is because first law and second law go together, and we use them to help solve problems. Right here, we don't know the mass or the acceleration. But is there a way we could find out one of those terms?
Yeah. The mass.
How can we find out the mass?
600 times 9.8. I mean, divided by 9.8.
Why did you say that?
Because you have to take the 600 in and divide it by the 9.8.
Yes, your math is correct. Because we have 600 right here. So they're both equal to 600. And then you said mass divided by 9.8. But why did you say divide the 600 by 9.8? Why?
Because you have to divide the mass from the gravity.
Why are you dividing mass from gravity?
To be honest, I don't know the exact word. I guess because of, I don't know. I have all these notes and I still don't know.
It's still F equal to MA, right?
Yeah.
Keep going.
Mass times gravity.
And what is gravity?
A force. A weight.
Acceleration.
Acceleration. Gravity is an acceleration. So remember how we did this? Anybody remember this part? Hold on. Actually, I just passed it. Look at this top one right here. When we talked about weight or force due to gravity, we could recognize it as mass times G. What is G? 9.8, which is an acceleration. So we can always find our weight by max times our mass times gravity, right?
Oh, because we're on Earth.
Exactly. So now we come here, right? Because I know that when I get here, I already know that my force due to gravity is going to be mass times the acceleration due to gravity. So now I can substitute this G in here for, like we said, 9.8 meters per second squared. Now I'm able to find out the mass. What's 600 divided by 9.8?
61.22.
61.22 kilograms is now my mass. So now we have our mass. So now with us having our mass, we can substitute this mass over here to find our acceleration. Because it's the same object, so it's going to have the same mass. So now I substitute that 2 over here, and I have my acceleration. Now I can just divide 100 by 61.2 kilograms. What's 100 divided by 60.2 kilograms?
$1.63.
1.63 meters per second squared. Now we could say negative, or we could say the direction of the acceleration is to the
Left.
left.
I have a question
Go ahead.
because I think I see where I was messing up at. Because I think my answers was a little bit off from what you have whenever I checked today for the earlier pages. And it's because I think I was subtracting 61.22 minus 100 instead of dividing.
Yeah, so that's just math. I wouldn't even trip on
So it's mass divided by the force.
hold on 1 second, please. All right, go ahead one more time.
No, I was saying I was subtracting instead of dividing, but on that for the answers, did you want us to put east, west, north, or south?
Like, so this one, right? Because technically, I think Cassie, you just said that you just asked about negative, right? Yeah, like if you say negative, what does that mean? Like, what does that mean? Like, how does that help me in the situation? You know what I'm saying? But like if you say left, like negative is not wrong, but it's like, how does that help with the situation? Left shows me, oh, I'm going to my right, but I have an acceleration going left. So it means I can know that I'm slowing down. Like in this situation, using the actual like turn left, right, or like you just said, if it was northwest or southeast or like those like type of things, it would give me better indication of what's happening due to the situation. Does that make sense? Did I answer your question?
A little bit.
Yeah, just like depending on the situation, right? It's not just about positive or negative. It's about actually giving insight of what direction like is happening along with the vector quantity.
Right, that's what I'm saying. So that's why I was asking. Like for instance, you have N, that means negative. So
Wait, hold on. Which one? This Newton's right here? This big N?
yeah, oh no, that's Newton's. So if
Yeah,
all we have to
big
do
N
is
is
put
Newton.
left or right.
Yeah. So yes. So the direction is the left or the right.
Oh,
The N
I'm putting
is Newton.
northwest. Oh,
That N is Newton's for the unit for that. Yeah. So like N, big word for Newton's for forces. So anytime you see a force and it has a N, that means Newton's. Does that clarify things for you now?
yes, thank you.
No problem. All right. Anybody got any more questions about this? Not because it's a bad thing. It's just this is like the foundation of like what we're doing today. Because it's gonna be more second law stuff. But like if you got the concept of how we went between first law and second law back and forth to find out answers, you'll be good. And my goal is to bring it all together with the third law too today.
I do just have one question.
Go ahead.
This is my last question, okay? So when it comes to the division part, if it's going to the right, do we multiply?
No, it's not about if it's going to like left or right, if you will multiply or not. It's really actually depending on the math, like how the equation is set up. Because it can still go to the right and you still have to divide. Like I'm trying to think, you'll see a situation, because this is basically just math. This is just a one-step equation, right? Because we're multiplying these two quantities, one times the unknown, we got to do the opposite of what we see and do that so that we divide. Now, if it was like divided and we had to find an unknown quantity, then we will multiply. Does that make sense?
Could you say that one more time? You said if it was what divided, we could multiply?
Yeah, if we were dividing, say if it was A, this A was divided by 61.2 instead of multiply. Like, because right here I'm multiplying. But if it was
Right.
divided, then I would have to multiply. That's not a physics thing, that's just a math thing. Does that make sense?
That makes sense.
Courtney, you good?
Hello?
I was saying, are you good?
Oh, yes, I'm okay.
Okay. Okay. Let me go see what's next. All right, so then we got another set of the same problem, right? Let me see how I go about this, right? Oh, I done gave the whole answer. My bad. All right. So now this one, let's try this one because it's a car, right? So sledding might have been a little, but I think a car should be easy. The brakes are applied to a rightward moving car and it skids to a stop, right? So I'll draw it on the board too as well. Let me just check and make sure nobody's waiting to get in. Hold on. All right. So I'll start my. All right. So I got a car, right? So let's think about it. What forces do we have present in this free body diagram? Throw some at me.
We have acceleration towards the right, or
Forces. Gravity.
we have gravity.
Tension?
We
What's
have
the
normal force,
force due to gravity?
9.8
9.8 is the acceleration, but the force due to gravity has a direction that goes
is a weight.
down.
Or down. I'm sorry, it's down.
There you go. So we got the force due to gravity, right? What other force do we have?
We have the normal
Why do you
force
say
going
normal?
up. Up.
So it has to have the opposite because we're not what? Say that backwards. Because we're not going into the ground, we have, there we go, the normal force, yes. Because we're not going to the ground, we're supported on the surface, so
Floor,
we have to
surface.
counteract the normal force. Now that normal force, how should I draw my arrow? Should I make it bigger or should I make it smaller or should I make it the same size?
You should make it the same size as the gravity.
I'm gonna make it the same size as gravity. So now, well, we making it the same size as gravity, right? Because these forces are the same size,
Equal.
they're, say it one more time.
They're balanced.
You said
They're
they're
equal.
equal, they're
Yeah.
balanced. So I'm saying that these are equal. So that means my up is equal to my down. And if these forces are balanced, then the sum of my forces is equal to
0.
0. This is first law. Newton's first law. Once again. Now, let's think about it again. We support on the surface, so we're balanced, let's say in the Y. But it says the brakes are applied to a right moving car. Brakes cause what?
Deceleration.
A deceleration, which is a what?
A force.
Not a force,
Hey.
but deceleration is a what? It's a type of a acceleration. So
Type of
acceleration.
acceleration. Okay.
So therefore, because acceleration is present, the sum of the forces is equal to what?
Is equal to.
The
Yes.
same thing?
Not the same thing.
It'd be different. The
M times A. What is M?
mass
Mass times
force.
acceleration. The acceleration, mass, the formula force is equal to mass times acceleration. Because there is acceleration present, The sum of the forces equals the mass times acceleration.
It's
Therefore, my forces are what? Unbalanced.
unbalanced.
This is Newton's
Second law.
second law. Now, what does that look like on my free body diagram? The forces are unbalanced.
The braking force should be, the force pulling the car to the left should be greater than the force going to the right, the acceleration to the right.
Is it accelerating to the right?
The brakes are applied to a rightward moving car.
It
So
would
the
be
car
left.
moves to the right. So if the brakes are applied and it's applied to a right until it skids to a stop, which direction is the acceleration?
To the left.
To the left. So the acceleration direction is to the left. Also, what direction is the force in? Like how we did our last problem, right? Acceleration is to the left, so the force is to the.
Right.
So now with this one, if our acceleration is going to be determined to the left, the force is at what? To the left. So now I can draw my force over here to the left. Now, the question is, what type of force causes me to stop or slow down? When I
Friction.
press the brake, say it louder.
Friction.
So now we know what type of force. We have a frictional force, right? Do we have any forces other present, or are we just good with these? We're good. So now we got our three forces present. We see that our forces are balanced in the y direction. Our forces are unbalanced in the x direction.
I have a question. You don't need air?
Huh?
You don't need air?
You could throw air in there, but I mean, like,
Air resistance does take
it's like, but
factor.
we keep arrow because we know like it's a car and it's braking. We could just go ahead and just use friction. But air
let's
is
just imagine there's a windshield over the car.
a windshield over the car. There we go. All right, so we got our three forces, right? I'm not saying it's always gonna be three forces, but this is just a balanced one, right? So there we go. That's how we create our free body diagram, kind of thinking about it logically, right? Now, let's just add some numbers to it. Hold on. So now we have the same scenario, right? Now we have our car and we have our F norm and our F grav and our friction. So all we got to do is just add some numbers to it, right? The weight of the car is 10,000 newtons. So then that means we have a normal force of 10,000 newtons as well, because it's connected to the what?
The surface of the road.
The surface. Yeah, the weight. Weight is a what?
Acceleration.
Not acceleration, it's a what?
It's a force.
Force. Forces are measured in what?
Newtons.
So even though it's weight, usually we measure weight in pounds, right? But weight is a force, you can measure it in newtons. Does that answer your question? What? Gravity times what? Okay, say that one more time. Gravity times what is equal to mass? Weight. So we know that gravity times mass is equal to weight, right? What is the weight? It's equal to the normal force, which is how much?
0.
1,000.
No.
Because they're both equal. We established that already. So now, because we know that, what can we find? The mass, because we know that gravity is equal to what?
9.8.
So I'm going to divide 10,000 by 9.8 and I get what?
One second, where's my calculator?
Is it 918, 36, or 37?
Say it again.
Is the-
10,000 divided by 9.8.
Yeah, 10,000 divided by 9.8.
I got 1,020.
1,020 even?
Mm-hmm.
Wait, it's what
0.4.
divided by?
Say it again.
0.4. 1,020.41.
What do we divide by?
9.8.
9.8.
No. What, why don't we
10,000.
divide 10,000 instead? Oh, because the gravity, okay.
The weight of the car is 10,000.
0.41 kilograms is our mass, right? Now, the sum of our forces is equal to what? In the y, it's equal to what?
It's equal to 0.
0. So that's out. But in the left to right, it's
It's
equal to what?
1,000. Oh, 9,000, my bad. Because there's only one. Yeah.
9,000. But it's equal to this. So now we know the sum of our forces is equal to 9,000.
1,000.
We need to find our acceleration. But do we know our mass?
Yes.
What is it?
10,020.41.
0.41.
Or 1,020.41.
1,020.41. Now we just divide here and here.
You divide our mass by our acceleration. By our Wait, what are we
Yep.
finding? We're finding the
Acceleration.
acceleration.
So now 9,000 divided by 1,020.41 is what?
0.11.
Do that one more time.
I got 8.82
8.82 meters
rounded up. Yep.
squared. Now, with our acceleration, right? We go into which direction from the diagram, it looks like.
Left.
Actually, we don't know. But what direction does it look like the force is going?
To the left.
To the left. So what direction we think the acceleration is going?
To the left.
To the left. So we'll just say 8.82 meters per second squared to the left. And the friction force going to the left as well. Let's see how we matched up on the answer. Does that look about right?
Could we say negative 8.82?
You could say negative, but would negative help us in the situation?
No.
We need to actually, in this one right here, we would probably want to know which way it's actually going. So that's what I'm saying. You can use negative, it's not wrong, but I think you get more information by actually saying left or right.
I agree.
Any questions on this?
No, that made sense. Using Newton's first law to go to the second law and vice versa.
That's exactly what I wanted to hear. I'm checking the chat too, just in case if nobody wanted to come off of mute. All right.
The sum of your forces is equal to your mass times acceleration.
More practice, right? So now, man, I cannot read that. We're gonna do the same thing, right? And we're gonna just keep practicing drawing these free body diagrams, but then actually solving them with the numbers. This is actually very important because it build us up to be able to do what is it called? Second law problems. All right. So, and reading this problem, right? We have a 30 force that's applied to a 20 kilogram sled, right? To drag it across some snow, right? And then we have an acceleration of 1.0 meters per second squared. We want to draw the forces acting upon the sled, and then we want to try and solve for them. Somebody, I need to let them in. Hold on. All right. So now what we having what is it? We have a sled. Matter of fact, we have two people in class today. So Victory, and Cassie. Who wants to draw the free body diagram? All right. So Cassie will draw the free body diagram on the board. We'll go over it, and then Victory will find the problem, the answers. There we go. And you guys will watch online and ask questions if you are confused or if you want to help out at the same time.
What was the prompt again?
So we have a 30 Newton force that's applied to drag a 20 kilogram sled over some snow.
30 newtons over snow.
Mhm.
Um,
So we got 30 newtons that's applied, drag 20 kilogram sled, and it creates an acceleration of 1.0 meters per second squared. So we got 30 newtons applied. So that's the first force you had, just the applied force. Okay. Now, are any other forces present?
Yes, there's going to be friction going this way.
Okay, we can say some friction.
And just going to put FF, and then there's force normal and force of gravity. These two are going to cancel out though. So we're just talking about these two.
All right. So you'll see why because we haven't gone deep into friction. So for right now, just leave friction off for right now. Not saying it's not present, but you'll see why, because they didn't give us a coefficient of friction. So we have how many forces present? 3. Okay. So now we have 3 forces present. Now what is having 3 forces present? What do they want? Okay. Now let's talk conceptually, right? You just said that those 2 forces that you just wrote cancel out. What does that really mean?
It means that they're balanced so that they don't have any relevance to the problem that we're solving right now.
They do have relevance. They tell us what?
They tell us, they would tell us then the weight of the objects.
I mean, the force of the gravity tells us the weight of the object, and then we have normal force, which is pretty much what?
Balancing it out. It's going to be the same thing.
So say it out loud. So they're balanced. So
They're
that means
balanced.
they're
They're balanced. So what are you looking for?
if they're balanced, their quantity is what?
Equal.
Equal.
I see.
So now their quantity is equal. Now let's think about this in context of what's going on. What is the actual problem? Or what's
The actual
happening?
Problem is, are we trying to find how much what
Not the math,
mass
like the
is?
situation.
Oh.
Like what's happening?
I see. It's being pushed at 30 newtons of force to create a 1 meter per second squared acceleration.
I don't need the math. So now it's being pushed to apply, right?
Okay.
But like what's happening with that? You say the forces are balanced,
It's not accelerating either up or down,
which means it's what?
which means that it's balanced.
It's balanced, but what does that mean towards it's not moving up or down? It's
moving to the side.
yes, but it's on up and down as what? It's on
It's balanced on the
Surface.
the surface. What's the surface they said? It was
No.
snow.
No.
So now
Oh, snow has less friction than ground, I guess.
so conceptually it's connected to
conceptually it's connected to the ground.
yeah, it's still on the ground.
Yeah.
So that's what that tells us right there.
Okay.
So now it's connected on the ground. The forces are balanced. So now getting back to the problem, in the up and down, which we consider the y, the sum of the forces should be equal to 0. So now we have some of the forces equal to 0 because the forces are balanced.
Yes.
But you said it's doing what? How are we traveling?
It's accelerating to the right.
Okay, accelerating to the right. So now when accelerating to the right, because acceleration is present, we have
We have an unbalanced force.
unbalanced forces. So now some of the forces in the left and right should be equal to what?
30 newtons.
30 newtons, right? So now what it's doing that, we know that the sum of the forces in the y is equal to 0. We know that the sum of the forces in the x equal to 30 newtons. How can we find the acceleration in the y and in the x?
Wait, I have a question. You said the sum of the forces on the right is equal to 30. I thought it said the applied force is 30.
So the sum of the forces, as in the net force. What are all the forces in the left and the right?
Also 30.
30 and 0.
30 and 0. So the sum of the forces is sum. I keep saying the sum of the forces because if you write the symbol sum, like the sum symbol, Yeah. And then write F. All of the forces, the individual forces present, and then write X underneath it, like the subscript X. And the left and right, or the X, is equal to right now 30 newtons. And why is that? Because it's 30 and there's nothing else.
I thought the like that symbol and F means what the net force, like
Net force. The net force is the sum of the individual forces. I just keep saying some forces because that symbol actually means some. And then F is
right,
40.
but the 30 is not that, right?
Think about it. The sum of the forces, say it out in English. The sum of all the individual forces the sum of the individual forces in the horizontal or the left and the right is how much?
30 because there isn't another force going in the other direction.
I thought there is another force. Isn't there friction?
I drew that and then he told me to get rid of it because we're not talking about that yet.
Yeah, because they didn't give you a coefficient of friction.
Oh, okay. Now that makes sense. I missed that part where you said you were not considering friction. Okay.
Yeah,
now
I didn't consider friction because
okay,
I don't.
okay. Then yeah, it would be the net force. Okay, carry on.
All right, so now we're there, right? So now you don't really have to figure it out, but like just conceptually, right? How would you go about finding acceleration if they didn't tell you that acceleration is present?
Well, if I had the mass of the object, I could just divide the force by the mass, and then I would come out to 1 meter per second squared.
Good. And then oh wait. All right, that's how we could do it. I think I could figure it out. All right. Real quick. This might actually go back to now. I think we can't find it. Say friction is present, right? Okay. Now, let's think about it.
Because we can still use the F equal to ma for friction, right?
Yeah. So now go back to what you just said. Because I was just thinking about it, but like it'll be fine. So now we know we have some friction, right? But how can we figure it out? We know the acceleration. What is acceleration?
1 meter per second squared.
And then we know that the sum of the forces is equal to mass times acceleration. Now, what you just said earlier, right? How could you find the mass
How could you find the mass?
of the object?
By dividing 30 newtons by 1 meter per second squared.
Wait, the mass is given.
The
Isn't
mass
it?
is given. All right. So now, with the mass being given, what's the weight of the object?
What's the mass?
20.
20. The weight of the object would be 9.8 times 20, which is like around 200.
Okay. So now we know it's about 200. I'm getting there. Just wait, hold on. 9.8. 200. Yeah. Okay. 200 newtons. And then you say the normal force is 200 newtons, but we know the mass is now 20, right? So now with that, I'm almost there.
9.8 times 20 is 196.
We don't need this, but I'm trying to figure out to make sure I have the friction is right. We know that the mass is 20, right? So the sum of the forces is equal to mass times acceleration in the left and the right, right? So now, the sum of the forces, write this real quick. The sum of the forces bless you, is equal to mass times acceleration, right? Now, we know the acceleration is how much?
It's 1 meter per second
One.
squared.
And now we know the mass is how much too?
20 kilograms.
20 kilograms, right?
So that means that it's 20 newtons.
So now we know the sum of the forces is equal to 20 newtons, right? So now, if the sum of the forces is equal to 20 newtons and we have a force, right? What are the sum of the, sorry, one step back. What are the forces that are present?
Force applied and force of friction.
All right. So now think about it. If it's moving and it's being pulled, which force, we call it winner minus loser, right? Which force is winning, which one is losing?
Applied is winning at 30.
So you would say applied minus friction is equal to mass times acceleration, or how much?
20 things.
20. So
So-
applied
Equals force applied minus force of friction.
friction, right? Because friction is losing. But we know how much the force applied is, right?
Yeah.
It's how much?
30. So equals 30 minus x or minus force of friction.
So then when you solve that, you have how much is the force of friction?
10.
10. So now we know that the sum of the forces that's in there should be 20 newtons. For some of the forces in the left or right, but friction should be equal to 10 newtons. And then we still have the same acceleration. What is the acceleration from that they give us?
Say that one more time.
What's the
It was
acceleration?
1 meter per second squared.
Okay, cool. So the one is really acceleration for acceleration, but also too, what's the acceleration in the y?
0.
0, because the forces are.
Balanced.
All right. That was a lot.
It just is kind of confusing when you say sum of all the forces, and I get that like technically it's that, but then you like subtract to get the net force, you know? It's just like flashes in my mind, the sum, and but you actually like it's the difference, not the sum, but maybe
Yeah.
it's because
I think it's like the difference between it's like the relationship in as far as the first law. Like if you add up two things and then divide them by two, and then you want to find the actual balance, which would be, are these things equal or not? It wouldn't it be easier to subtract? I think that's right, Professor?
Say the last part of your.
When you're finding the balance, it's better to subtract to see if they're equal or if they go out to zero.
No, you really just adding. Like adding and subtraction go together. The only difference is like when you start talking about like direction, even when we say some of the forces, right? When we
Mhm.
start adding the negative, we just add a different direction. So we say they're going opposite directions. So technically, like, go ahead.
okay. So if we want to call it the sum of the forces, then we need to make sure the negatives are in there, right?
Yes, because that gives the direction. Like that 30 newtons is say the direction is just whatever, right? We're going to the right. We know it's frictional force going to the left. So we have to add a negative because it's not going in the same direction. Because if it was going in the same
makes
direction, it would be added.
Yeah. So like the sum of all the forces include the signs, and then if you say net force, in my mind, that's like just the magnitude difference. Okay.
Yeah.
Got it.
Net force, if you think about the magnitude difference, and you see some of the forces, just add a make sure you have a negative sign. It's the same thing. Because if I flip that 30, if I keep that 30 the same and I flip that negative 10 to a minus 10, I'll still get 20. So it's the same thing. All right, let me see what the next one is. All right. Guys, I just made you do the whole problem, so I'm gonna have Victory come to the next one. Sure. Come on down. All right, so let's talk you through this one. So we have that first one was kind of like sledding. Like I try to keep doing the same problems where it's like the same thing with like sledding and like cars. So this one's a car problem, right? So we have a car that's 800 kilograms and is coasting to the right with the leftward acceleration of 1 meters per second squared. You want to draw the forces acting upon the car, and then we're going to solve for them. So we got a car and it's going to the right with a leftward acceleration.
Going to the left.
times did it say?
It's going to the right with a leftward acceleration. So think about that. It's going to the right with a leftward acceleration.
It's moving to the right. but- Okay, so it's decelerating.
Okay.
So what's the acceleration?
So think about it. If it's, you said it's decelerating, how's a car decelerating?
It slows down.
How?
It's so like the brakes.
So you're pressing the brake, which causes,
It's a slow down.
yes, it needs a what to slow down. It's acceleration, but it needs a what to cause the acceleration. What causes acceleration?
An opposite. Oh,
Of-
acceleration.
Of
Force.
force. So what type of force would cause acceleration for a car?
Friction.
Friction. So what force would we put right there?
Friction.
Okay. And that's just going left and right? Now is a car float in the air.
No.
So if it doesn't float in the air, what happens?
Oh, we need gravity. And normal force
Because it's connected to the what? The
connected to the surface.
surface. There we go. So we have the force due to gravity. And then we have the now let's see if it said anything else. It just said a car is coasting. So coasting is going at a regular speed, but then it starts to have a leftward acceleration. So you can just imagine the brake. So it's not any like push or anything on the force. So you think we go with that?
Is there anything that's pushing it forward?
Think about it, it's coasting. So if I'm coasting, you drive.
No, I don't drive.
Okay. So you ever heard of cruise control?
I have, yes.
So like I would just literally, I could take my foot off the gas and I could
And
just
it
like
would
leave it
just
there.
go.
So think about it. Is my velocity changing?
No.
No. So am I touching the gas?
No.
No. So I'm just not applying any.
Any force.
So it's just the what's force?
The
That's-
friction.
Friction. It's making me slow down.
But would it have to be? Oh, if it's slowing down, then it will be unbalanced, right?
Oh, okay. So if the forces are unbalanced, then what do we know?
We know that
There's an acceleration.
There's an acceleration. And the sum of the
of the force
is equal to,
is equal to mass times acceleration.
there we go. Now in which direction specifically?
Left
Left and
and right.
right, which is technically X or Y.
X.
There we go. So now we know that, right? Then in the Y, what is the sum of our forces equal to?
0.
Because the forces are,
Balance.
there we go. Now for this one, right? What forces do we have present in the X and Y? Sorry, in the Y.
In the Y, we have normal force and gravity.
What's the forces present in the X?
Friction.
So what is the sum of the forces in the X? How can we figure that out?
We know that the sum would be whatever the friction is.
And the friction is equal to,
Did it say?
it didn't say, but can we find it out?
Mass times acceleration.
Do we know the mass?
Yes.
How much is the mass?
800. 800.
Okay. Do we have an acceleration?
Yes.
It was how much?
9.8. So
Hold on. What is that?
the acceleration.
Yeah. What was that 9.8 you just said?
That's the gravity.
Gravity.
But this one's going left, not down.
Gravity is in what direction?
Down.
Down. We're talking about what direction right now?
The left.
So is there gravity present in the left?
No.
No. So what is present in the left?
Friction.
Friction, which causes a what? A word.
Acceleration.
Did they give us an acceleration?
I have a question. I thought friction caused deceleration.
It gave us
The
one.
acceleration is just acceleration in the opposite direction, so you slow it down. But yes.
Oh, leftward acceleration.
Yeah.
Okay. So it's 800 times 800 newtons
Newtons or
Is it not units?
forces in newtons,
kilograms.
kilograms. There we go.
Times,
So the sum of the forces is how much?
800.
There we go. So the sum of the forces, which is really just friction, is equal to how many newtons?
800 newtons.
800 newtons. And then the sum of the forces in the y is equal to.
0.
So now because the sum of the forces in the y is equal to 0, the acceleration is equal to.
0.
That makes sense to
The
you?
acceleration is
Yeah,
0?
and the y,
Oh, yes, it's 0.
0. Okay. Does that match up what we have right here? Did we get the same answers?
Yeah.
There we go.
800.
Okay. Good job. Any questions about that? Did I skip?
I don't really understand, but I guess I would just have to practice some more because I
No,
really
no, 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 no. What questions do you have? Where are you stuck at?
So I get that it's the normal force and the friction and the gravity, but it's the X and it's the X and Y.
When I say X and Y, what does Y remind you of?
The right,
That's it right
like
there.
the line, like the horizontal line.
When you plot a graph, is the Y vertical or horizontal?
Oh no, the Y is vertical.
There you go. That's what Y means, vertical. When you plot on a graph, X. Which
Because I'm trying
actually
to look at the 1 meter per second left. Like whenever they say one. Okay, I get it. Okay.
was that it?
Yep. Thank you.
No problem. All right, now we here. The reason why, which one was this? Is this friction? All right, cool. So when I was talking about that previous problem, right? I wanted to make sure before I started talking about friction that we understand that you can find friction based off of the coefficient of friction. The coefficient of friction, this is mu, right? This is called mu. This stands for the coefficient of friction, and what it means is each different surface has a certain like a number to represent how much, so you can calculate how much friction it creates for basically for it to slide across. The frictional force that we have, right? So how much friction, like how much force caused due to friction, is equal to the coefficient of friction times the norm. Was it divided by the normal force? Did I say it right?
Times the normal force.
No, I think I divided. I just didn't finish that. That's a typo. It should be divided by the normal force. I think so. I didn't type that right. My bad. Hold on. Yeah, it's mu times the normal force. Is equal to the coefficient times the normal force, right? Now there's different types of frictions, right? We have static friction, sliding friction, and like rolling friction, right? But really what we want to go ahead and focus on is how to calculate friction in different ways, right? So let's just do this one real quick. This shouldn't even be too crazy, right? We want to use the friction equation that we have over to the top right, right? Mu times the normal force, right? To be able to fill in the blanks. So as we go through this, right, let's do this more conceptually without this actually like trying to do as much math. Remember how we were going before earlier when we were doing first law and second law and kind of going back and forth? We need to be able to do that to be able to help us find out the coefficient of friction, because what do we need to find out the frictional force? What quantity?
The normal force.
Normal force, right? So like in this first one, right? Let's look at this first top one. They actually gave us a normal force. So let's think about it. Let's talk it through. We need to find the frictional force. We have a normal force, but do we know mu? We don't know what mu is. Now let's think. The acceleration is 0 meters per second. What does that mean conceptually if the acceleration is equal to 0 meters per second?
Forces are balanced.
Forces are balanced, right? So what does that mean if the forces are balanced?
It's not moving in any direction.
No. It's not that it's not moving. It's moving at what type of
Oh, a
rate?
steady pace. A
Steady
rate.
pace, constant, is maintaining a state of motion. So it's maintaining a state of motion, the forces are balanced. So the forces are what? If the forces are balanced, they're also
Equal.
equal. So if there's no acceleration present, that means the forces are equal. So if the forces are equal, can we find the frictional force?
No.
Yeah, because it would be the same as applied force.
Exactly. The forces are balanced. So now that means that the forces are equal. So now that we know that the forces are equal, we can say the frictional force is the same as the applied force. So therefore, the frictional force is how much? One more time, the forces are balanced, right? So because the forces are balanced, that means that the forces are also equal. We know the applied force, and we know that that's equal to the frictional force. So the frictional force, therefore, must be how much? Say it loud.
0.
10 newtons. Good.
Oh,
So now that we know that frictional force is equal to 10 newtons, now can we find the coefficient of friction?
yes.
How will we find the coefficient of friction?
By doing u.
Look over to the right? You see my mouse? Friction
Oh, I
is
had to
equal.
zoom. I had to zoom in. My bad. UF norm.
Do we know this? How much friction is?
Do we know? No.
Yes, it's how much?
Or 10 newtons.
10 newtons. Do we know how much F norm is?
F norm
12 newtons.
is 12 newtons.
So how much can we find the coefficient of friction?
By dividing the frictional by the norm,
And we get what?
we get the coefficient.
Which is
10. Is it 12 divided by 10 or 10 divided by 12?
It's 0.83.
okay. And this is one thing that we should know too. The coefficient of friction is always between 0 and 1. So you should never have a number bigger than 1. So the point that you got 0.83 is good.
So can I just go back for a second because I want to make sure I got the. So you still do 12 minus 12, right? And then you do 10 minus, I don't know what, 0 or 1 or Z. I always say 0.
Take a step back. Don't worry about the numbers. Walk it through with me. The acceleration is equal to 0. What does that mean when there's no acceleration?
It's at rest
Or it's
in
moving with constant what? V word.
velocity.
Velocity, right? So if it's moving with constant velocity or it's at rest, the sum of the forces are what? Balanced or unbalanced?
Balanced.
Balanced, which means the sum of the forces is equal to
The same number, 10.
10. Yes. So now it's the same number. So friction is equal to how much?
10.
10. So now because we know friction is equal to 10, can we find mu knowing that friction is equal to mu times the normal force?
If you
I don't
Hold
really
on.
understand mu, I think. So I don't know.
Wait. No. You don't got to understand mu. Look at the equation. We got 3 quantities. Do we know 2 of the quantities?
Yeah.
So if we know 2 out of the 3, we can use those 2 to find the third.
Which is 12 minus 12.
Not 12 minus 12. Friction is how much?
10.
10. How much is F norm?
So 10 times 12
Hold on. How much is F norm?
is 12.
12. So now I have hold on, no. I'm here. Just wait a second. Why are you disappearing after I'm writing? Okay. You see this?
Mm-hmm.
Yeah, just looking at the screen.
Yeah, I'm looking.
A good way I like to remember is it's like kind of solving for x. If you need, look at the equation. If you need the coefficient
We need
by
this.
itself,
It's not coming up on yours. Are you able to see it?
Yes. I can see your hand.
You see this green ink?
no,
Yeah, I can see the green. I can't see the green ink, but I can see a green dot.
we
Hold
don't
on.
see anything. We don't see anything green.
Let me see. Do you see me doing this at the top?
Yeah, I see you moving that around, but there's nothing on being left.
Anything on the now? All right, hold on. Now?
I'm not seeing anything.
That's annoying. You see this?
I just see a mouse.
I'm actually confused at why it's not coming up. All right, that's fine. All right. Do you see the board?
Mm-hmm.
We know that frictional force equal to mu times the normal force. We know that the normal force is equal to 12 newtons, and we know that frictional force is equal to 10 newtons. But we don't know how much mu is. So what would I do? Or what can I do? I know this one, but I don't know this one. I could do what?
Subtract,
You can,
Not subtract. I could do what?
divide.
Divide. I'm going to divide this by 12, this by 12.
make it
A3.
You divide what by 12?
10 divided by 12.
Okay.
a good way I like to think about it is if you do like 10 is equal to x x times 12, and you need to get the x by itself, what do you do?
We're just finding for the unknown like we did in the last class, so it's not that
Mm.
difficult.
Not a diff. You bring 12 over and it'd be 10 over 12. And if you do 10 divided by 12, that would be the 0.833.
Does that make sense?
That's how I remember it. I just turn it into algebra. That's the reason why we're dividing it.
Are we good with that? Or Do we need to keep going? Any objections? We good?
Nope, all good.
All right, so they got that first coefficient, right? Let's do the same thing. We got this 3 more times. Actually, yeah, why not? Give me 1 second. There we go. Okay. Give me 3 of them. So we just did the first one, right? Real quick, I'm just randomly putting y'all in here. Take 2 seconds to go ahead and try out to find the coefficient of friction for the first one, the second one, the third one. If you're in the main room, try and join your breakout room real quick. I'll give you guys a couple seconds. Terry, did you raise your hand? Oh, hold on, sorry. Let me share one more time. So it might have got a little funky, but that first group, did anybody get anything for the top right?
No, we didn't. I think we were kind of confused.
All right, let's walk through it.
I got 6.1.
For the first one?
For the top right, yeah, top right.
Okay, top right. Try and talk me through how you got 6.1.
Um,
Seth, you still there?
yeah, let me open my note real quick. So I take the force friction is equal to the force normal time the how do you call that sign again?
To mu.
Yeah, the U. So it's 0.51. So I take 12 times 0.51, then yeah, I got 6.1.
How did you get the 0.51 again?
Yeah, I didn't understand that because I thought it was supposed to be 12 divided by 9.8.
Sorry, I was on mute. To find out mu, we need 1, 2 quantities. Right here, top right.
We need the force friction and force normal.
All right. So out of these, right? What quantities do we have? Do we have force normal?
We do.
Yep,
It's how much?
it's 12
12.
Newton.
Do we have the frictional force?
No.
No.
No. How could we find the frictional force?
I'm gonna use force equal ma.
Why can we use force equals ma?
Wait a
Look at
minute.
the free body diagram. What do we know about the forces? They're what? Unbalanced. So now since they're unbalanced, we can use force equals mass times acceleration. Do we have an acceleration?
Yes,
And it's
12.
what?
5.
5 meters per
Oh, my
second
bad.
squared.
5.
Do we have a mass?
No,
12. We have 12 newtons.
We have 12 newtons, but do we have a mass, which is in kilograms?
Oh, no, we don't.
Can we find a mass?
Yes.
How will we find the mass?
We would divide the 1 second, 1 second.
Wouldn't we divide 5?
5 is the acceleration. We need a mass. But what can we do with the F gravity? F gravity is what? It's also called what?
Oh, an acceleration. We can
Mass?
do the newtons divided by gravity.
And we get what?
1.22.
1.22. So now that's our mass. Now we have a mass. Now what can we do with that mass?
We can times it by the acceleration to get the net force.
For
One
The
second.
force friction.
The force
Now that's
friction.
what?
That's 6 newtons.
6.1.
There we go. Okay, so we got something. I'm really looking at the method, but the method sounded good. All right. Do you see how we went about it, right? We had to find the force of friction to be able to find the coefficient of friction. We still need to go ahead. And now that we know the force of friction is how much?
6.1?
6.1.
6.1.
6.1. Now what is the coefficient of friction? Or mu?
And you take the
6.1.
friction divided by normal.
And you
When
get
you
how
take,
much?
you would get
0.
6.1 divided by 12. 1 second.
0.51.
There we go. I'm not even worried about the numbers. I just want to hear the method behind
Yeah.
it. We'll look at the numbers in a second, but the method behind it sounds good, right? Can I get that next group? Bottom left.
We weren't finished working through it, but
We got
I
the 6.1.
What
I
is 6.1?
understand it.
We got 6 for net force, and we were about to find out the frictional force.
Okay, so how did you get 6 for the net force? Talk to me.
We did mass times acceleration,
Mhm.
and to find mass, we did force of gravity divided by 9.8,
Mhm.
and that was 1.2. So 1.2 times acceleration was 6,
So that's the what?
like the net force.
So now you know the net force is equal to, let's say 6, right?
Mm-hmm.
But net force is the sum of all the forces. How many forces do you have present?
2, applied force and frictional force.
So the sum of those forces is equal to 6 something, right?
Yep.
Are those forces going in the same direction?
No.
No. So the sum of the forces is equal to 6.
The
And
forces are unbalanced.
the forces are unbalanced. Now the sum of the forces are equal to mass times what?
Acceleration.
Now, the acceleration is in what direction?
Right. So that
Right.
would be positive, and the other one would be negative.
Right. So now, but knowing that, right, how much would be the frictional force?
-6.
Hold on. Think about it. The sum of the force is equal to 6. The applied force is equal to 16.
So it would be like 10 or
16,
negative 10.
Oh, 16
16
minus 6.
16 divided by 6.
Oh, 16 divided by, yeah.
Hold on. Slow down. The sum of the forces. When we talk about sum, we're talking about what operation? Addition or
Mass times
subtraction?
acceleration. Oh, 16 minus 6 is 6. The answer still, the answer would
Sum of
still
the
be
force.
6. It's 16 minus 6.
Which gives us what?
Yeah.
Say it louder.
16 minus 6 gives us 10.
Okay, so we're around 10, right? So now we're around 10. Do we have a frictional force? Do we have a normal force?
Yeah, it's given, it's 12. So it would be 10 divided by 12,
Which is how much?
0.83.
Okay.
That sounds about right because we had that in the first problem, right?
Wait, now I'm confused. So it's 16 minus 6 equals 10. And what do we do with the 10?
The 10
We
is the
divide
frictional
that.
force. We divide that by the normal force to find the coefficient of friction. Which we just found was 10 divided by 12, which is 0.83, which is what we had in the first problem. The only difference is in this problem, right? We do have a frictional force and an applied force. They're just not the same. They're not balanced. Similar to what
Okay.
we seen earlier. All right. My last group. Anybody get anything for the last group? Bottom right. If not, we'll just do it together. Anybody? All right, let's take our time with the last one real quick, right? So we are trying to find the frictional force and the acceleration. So we know that mu is equal to 0.5, right? So friction is equal to mu times the normal force. Can we figure out how much friction is?
Yes,
Because we have mu and what?
the applied force or
Applied force or
the normal force. I
the
mean,
normal force. So mu times the normal force is how much? We got 0.5 times what's the normal force?
12.
12. So 0.5 times 12 is how much?
6.
6, right? So the frictional force is equal to how much?
6.
6 what?
6 newtons.
Newtons, right? So now we got 6 newtons on the left and how many newtons on the right?
30. They're unbalanced. So it'd be
Unbalanced, right? So which one
6
is
minus
technically
30
winning? Yes.
or 30 minus 6,
30 minus 6. So 30 minus 6 is how much?
24.
24. How can we find acceleration?
We do the mass, or we do, one second. We
Talk
do
me through what you
force
do.
over, we do force over mass.
And we get an acceleration, right?
Yes.
Do we know the mass?
The mass is 12, or no, we don't know the mass yet. This
Can
is
you
where I
find
keep
the mass?
messing up because I keep forgetting to convert to kg. You need to do 12 by over gravity, so 12 over 9.8.
And you get what?
1 second, 12 over 9.8, 1.22.
Now that we know the mass, can we now find the acceleration?
Yes.
Because we know we know our net force is how much?
Our net force is 24.
Because how did you find 24? You did what?
You did 6, which is the frictional force, or you did 6 is just frictional, or 30, which is the applied force, minus 6, which is the frictional force.
And you got how much?
24.
And because they're imbalanced, the sum of the force is equal to what?
The sum of the force is equal to 24.
Yeah, the sum of the force is equal to 24, but when we have unbalanced forces, generally the sum of the force is equal to what? The equation at the top right?
Oh, mass times acceleration.
Good. So do we know the sum of the forces? You said it's how much?
24.
24. Do we know the mass?
The mass is 1.22.
So now can we find acceleration?
Yes.
How would we do that?
We do force over mass. So it'd be 24 over 1.22.
And we should get how much?
Over 1.22 is 19.67.
And now I need a direction. What direction would it be in?
1 second, it'd be going towards the right.
Why do you say the right?
The applied force is bigger.
Applied force is bigger.
It's going towards
All
the
right.
right.
See how we fared out. Do these numbers look right?
Yes.
I don't know why they don't look right, but I guess. And
Well, the
feel like
one I just
did
did looks right.
Which one don't look right to you?
the one that we did, because we didn't get 0.82.
We got 0.83, which is very close. I feel like that's within margin.
I don't think I calculated.
What did you get?
I got, I don't know why.
Thank you so much, Professor. You made me figure out where I kept going wrong. I keep forgetting that you have to find the kg.
I got 10.
Oh, yes. You have to definitely, when you find in the mass, you got to do it in kg. You're finding kg, yes, the units. Courtney, you got 10 for the frictional force, which is correct. You just got to go one more step further and get the coefficient of friction, which is 0.82.
So you need to do 10 divided by 16.
12.
Or
Okay.
12, I mean.
I
You
will
just
be
had
10 by 12. I did 10 by, I had 10 minus 16.
Yeah, no, 10, we got the 10 from the frictional force, which was 16 minus 6. Then you got 10, which is the 9.9 that you see right there. Then you got to divide that by 12, and you get 0.82. Does that make sense?
That makes sense to me.
Hold on, I'm writing it down. I was trying to rewrite it over. Give me a second. But it is-
It's all algebra.
So I do have 10 divided by 12 right here. Okay.
There you
I just
go.
think the answer.
All right. Let's see if I keep going. Okay. Take 5 minutes. We're gonna come back. We still getting out of here at 8:30, but I definitely want to finish this. But take 5 minutes, okay? All right. I don't know if that was 5 minutes or not, but I'll just come back because I want everyone now. Yeah, I'm still recording. All right, okay, cool. We're gonna talk a little bit about air resistance, right? So now we did just talk about friction, right? Where friction got us leading up into understanding like how you have some type of resistant force that goes opposite the direction of the motion, right? So friction is more on the surface, right? But like air resistance, right? It applies when you're going through the air. Like say if you're driving a car, you can feel the air resistance here, or when the real present one is like free falling action, right? So if anyone's heard of like we'll thought about like skydiving, right? You skydive or you jump out of a sky, like you know what I'm saying, like you fall in and you go ahead, you do the parachute, right? That parachute catches all the air to be able to kind of slow you down so you could like land gently, right? So that whole idea builds off the concept of forces with air resistance, right? And that gets us into talking about this thing called terminal velocity. Once you get your air resistance equal pretty much to your weight, then you hit terminal velocity.
Wait.
Go
Is
ahead.
this? I wanted to say it. Is this correct? As an object moves faster and faster, the amount of air resistance um decreases or increases? Decreases.
Not so much it's not because of the object moving faster, it's more so the surface area directly related to the surface of what's hitting the air, right? So think about the parachute, right?
Mhm.
As it gets bigger, like as you let it out, right?
Mhm.
It gets to be a bigger surface area, and there's more air hitting that, to where then it pushes up on there to where now you have the cross sectional area to where now it's applying more air resistance force.
So the amount of air resistance increases until the state of terminal velocity is reached.
Yes.
Once terminal velocity is reached, the force of air resistance is equal to the force of gravity. Hence, the
It'll
object will
be what?
stop acceleration
Because it's what?
because it's a balance force.
Balance forces. That's important right there. And that makes sense because do you want to be accelerating when you're about to hit the ground?
No,
No, you want to be going at the same constant rate so that your body can absorb the fall and you can hit the ground and you can be fine and not crush.
okay, that
Now,
makes sense.
think about that in terms of, hold on, just gave the answers. Air resistance, right? So now let's look at it, right? This one is more conceptual, right? We want to know how the air resistance will look at A, when they just jumped out, and the E, when it's reached terminal velocity. So A, when they just jumped out, right? How much air resistance do you think they'll have?
Not a lot.
Not a lot. So the arrow will be small or big?
It'd be small.
Small, good. Now let's think about that N when it's E, right? Will the arrow be small or big or the same?
It'd be big.
At
The
E,
same.
the same. Will you reach
Or
terminal velocity?
when you reach terminal velocity. Okay, so it'd be the same.
Okay, so now at B, C, and D, how will we see the arrow changing? Will it be increasing or decreasing?
At B, it would increase. At C, it would increase, and maybe at D, it would start decreasing, and then at E, it would even out.
I say
What do you mean
decrease.
by what do you mean by decreasing?
Or
It would be.
never mind. I guess it increases until it equals. My bad.
There we go.
So it's steadily increasing from B, C, D until it reaches equal to.
Is that what you see here?
No, I thought it was decreasing in the beginning. I thought B, C, and D
That is
was.
that's what we see. We see it increasing over time until it's equal.
One more time. When it comes out, do we have a lot of air resistance when he jumps out?
No,
When we reach terminal velocity, what does that mean?
the air resistance has equal to the force of gravity.
Which means what? The person that's falling out the sky is doing what?
Stops its acceleration.
Stops the acceleration. So now, after we get to that point, right, how is the force of air resistance changing?
It's pushing up.
It's
Which
increasing
means it's what? It's increasing until it reaches what?
equal to.
Terminal velocity.
Yes. So we're increasing until we reach to or equal, which causes terminal velocity. Now take that concept, right? and we're going to apply it right to free falling, right? So we have a couple different cases, right? The same thing, right? We got a 90-kilogram skydiver. He jumps out of a helicopter at 6,000 feet above ground. And we want to use the free body diagrams to represent the direction and strength of the two forces. For each diagram, let's apply Newton's second law and determine the
Riding to
acceleration
school
value.
and with no shoes on.
Say
When
it
my
again?
life is house shoes, I better not ever see them outside. I'm sorry.
Oh. All right. So now let's go and let's start at the first one. Let's actually do this one together, right? So based off the free body diagram, we're just adding here. Is there any, we just jumped, this one right here looks like what? The first one. What scenario? Remember from the first one? A, when they just jumped out.
That's when they just jumped out. Yeah.
They just jumped out, right? So now let's look. So when A, they just jumped out, right? So what
So
do we expect the acceleration to be?
Could you say that again? What do we think the acceleration would be if what?
They just jumped out. We're looking at the free body diagram.
Which
What force is present?
which part are we on? The 6,000, like the first slot, the first block?
Yes. Yes.
0? No,
Hold on real
no,
quick.
the acceleration would be 900.
The acceleration to be 900, or what is that force?
That's the gravity. That's
The gravity
That's force.
would be-
That's force.
But the
gravity.
one pushing up, air resistance will be 900 too.
Is there air
No, not
resistance
yet.
right there?
Not yet.
It's still pushing up something. It will be some force that's,
Look at the diagram. We just got out. We just jumped out.
When he
The air.
just jumps out, we're saying there's no air resistance.
there's
Now
no air
there's-
resistance, and that means acceleration is full throttle.
Okay,
Which
so
is
now
just-
with that, how much is the acceleration?
We have to
6,000.
do 900 newtons divided by gravity to find the.
What do you say?
Do we don't we have to find the mass to get the acceleration?
You have to find the mass, so you have to divide what by? Say it again, Victor.
900.
Who? 100 by 9.8.
Yeah,
Victory said we have to divide 900 by 9.8, and we get how much?
I just think why.
We got 91.83 or 91.8.
Oh, we didn't even have that because of what you call. I'm tripping. My bad. The kid it gave us the mass. It already gave us the mass. So now we can actually find acceleration. The acceleration is due to what?
Oh, the mass is 90 kilograms. I see.
It would
So
just be
accelerate-
gravity.
Yeah, it's just gravity. So that first one is just gravity.
Okay.
So you can put 9.8 or you can put 10 to estimate it. It's fine. All right, go to the next one, right? So now the next one, what do we have?
Air resistance of 200 and
Newtons.
gravity of 900, so it will be unbalanced.
So now that it's unbalanced, right? Which it was still unbalanced, but it's unbalanced, right? So now we got to find the net force. What is the net force? Or
The sum of all forces.
It'd be 700.
700. Good. So now that's equal to how much? I'm sorry, it's equal to what?
That's equal to the sum of all forces.
Yes, and because they're unbalanced, it's equal to what?
Wait, 700.
700, but it's equal to also to what equation in the top right?
Mass times acceleration.
Mass times acceleration. What is the mass?
700 equals the mass. The mass is 90 kilograms.
So what's the acceleration at this point?
700 or 90.
Divided by
divided by 90, which is what?
700 divided by 90 is 7.7.
7.78.
Mhm.
Okay.
I have a
I'm only
question.
repeating because Victory is saying it in class. I don't know if I can hear her, but go ahead.
7.78. That's what I got.
Okay, my whole thing is this. I mean, I know it's like probably so elementary to ask, but we wouldn't do 90 divided by 700.
No, that's not the way to get.
So it's always the
net
biggest
force.
number on the top, right?
No,
No.
it's whatever quantities.
The quantity changes based. So the force of gravity never changes, but the opposite force changes based off situation. It could be air resistance, it could be friction, it depends on the context. But in this context, as he's starting to get distance from the helicopter, he's gaining a little bit of air resistance. And at this point in his free fall, it is at 200. That is
Hold
my
on,
understanding.
because
of
I
it.
don't think you was understanding what I'm asking. My thing is okay, we got a 700 net force, right?
Yes.
Okay, so
Right here.
Professor, can you hear me?
Do you see the board?
Yeah.
What you're asking is this. We got to this point. We did some math, physics. And we got 700 here. We know that the mass is 90. And we want to find this. Because we want to find this, we have to divide over here. To leave this by itself so these cancel out. This is math. So then we get the 7.78. Does that make sense?
Yeah, I really can't see, but it's okay. Yeah.
Yeah, so we just have to divide on that side because we're trying to find acceleration. It's not the biggest number, it's just whatever quantity was unknown, we divide by that.
Okay.
All right, so go to the next one. Try that one. What do we see?
We see equal forces. They have reached terminal velocity.
So we see equal forces. Therefore, the forces are what? Balanced.
Oh,
So when the
balanced.
forces are balanced, the sum of the forces, the individual net forces is equal to what?
0,
0. If the sum of the forces is equal to 0, acceleration is also equal to
0.
0. There we go. Go to the next one.
Forces are unbalanced now.
Unbalanced. So now the sum of the forces is equal to how much?
1100 minus 900 is equal to 200.
200. Okay. So now the sum of the forces is equal to 200, but it's also equal to what?
Mass times acceleration. So we would
What is
divide
the mass?
200 divided by 90 kilograms. We get
we got acceleration.
2.22.
Good. Go to the next one.
2.22. 1 second. Okay. The forces are again unbalanced because he has opened his parachute and he has gained even more air resistance. 1500
600.
minus 900 is 600. 600 divided, or 600 is equal to mass times acceleration, and that would be 60 divided by 90, and we got 6.67.
To the last one.
The forces are equal, so the sum of the forces are 0, so the force is balanced, and therefore the acceleration is 0.
All right. Okay, cool.
Hold up,
So
wait,
now-
because I missed the one before that because I was still writing. So it's 1100 minus 900, right? So that's 600.
No, that's 200.
I mean,
1100
no. Sorry, 1500 minus the
minus
900.
9 is
Okay, so
600.
yeah.
600.
Hold on. You was talking too fast. So 1500 minus 900 is 600. So
Yeah.
then the 600 is the sum of all the net forces. So it's a
Yes.
net force. Okay,
Yes.
I got that part. And then after that is whenever I got kind of mixed up because it's mass times acceleration. So it'll be
So do 700 is equal to 90 times A, and then put A by itself. How do you solve that equation?
hold on, wait, what? Wait, see, hold on.
Do 700, which is
No,
the
wait,
net.
because it's not 700. That's
I mean,
what I'm saying.
600, my bad.
Yeah, hold
600.
on.
600, which is the net force, equal.
Hold on, wait, because I'm trying to write it down. So my question, because this is where I keep messing up at. That's why I need to hold on real quick. So, Professor, because it seems like I keep making the same mistake right here, and I don't know why. Maybe you can help me out. After I get the 600, I don't know why I would do 90 times.
Acceleration times A, because that's the formula.
No, what I'm saying is what is the acceleration?
We are
That's what we're
finding
finding.
that. Wait. If you do the equation I'm trying to give you. Write 600 and then equal to 90 times A. Now solve for A. How do you solve that equation algebraically? How do you isolate A on
That's
one
what I'm
side?
saying. So it'll still be 90 divided by 600.
No, it'd be
Okay.
600 over 90.
I don't know. Maybe that's where I'm messing up at. I guess I'll just have to get some extra help.
You're messing up algebraically.
Yeah, that's what
Yeah,
I'm saying.
this is math. That's not you did the physics part right. It's the math. You have the A on the right side by itself. Sorry, A with the 90. You want to find A, so you have to divide by 90 to
On
get
both
rid of the
sides.
90 on both sides, so that you could just have A by itself. So that's why you do 600 divided by 90. So then when at the very end, you'll have A is equal to whatever number you get. In this case, it's 600 divided by 90, which is how much?
Wait, 1 second. 600 divided by 90 is 6.67.
Yeah.
Okay, so that's why I was just trying to make sure. Okay, now I see where I'm messing up. Okay.
Anytime you get that net force, when you subtract, the air from the gravity or the friction from the the applied force, that number will always equal mass times acceleration. And if you need to find the mass, you put in the acceleration and then you solve for m. It's the same thing.
Okay, because I get that part. It's like you said, it's just my algebra. So I see where I'm messing up at. And I'm just the type of person that have to practice more anyway, but I get it now. I got it. It's just I don't have the right answers because I see where I'm messing up.
But this is physics, so it's okay, because now we want to talk about what these numbers even mean, right? So now look at these questions that go along with it. They're asking what two altitudes has a skydiver reach terminal velocity? Now think about it, right? What does it mean when you reach terminal velocity?
The forces are balanced.
Which means that,
Acceleration is at 0.
so
you've
which
reached
two altitudes do we have terminal velocity?
4,500 feet and 1,500 feet.
Good. Because of what? What was equal to
Because of
0?
the
they're
acceleration is
balanced.
equal.
And the forces are balanced. Good. So at which altitude is a skydiver in a state of speeding up?
Only at 6,000 feet.
Okay. Well, yeah, I guess. And then what other altitude is a skydiver in a state of slowing down?
I would say 1,500 feet,
3,000.
3,000 and 2,900.
Okay. Now, at 2,900 feet, the skydiver is doing what?
At 2,900 feet. 1 second.
He's coming down.
He's slowing down.
You got to choose two.
Wait. He's choose two. Wait. He's
slowing
moving
down.
downward
Accelerating.
and slowing down. He's moving downward and slowing down. Or actually, he's moving upward.
The air is
because
pushing him up, but he's moving down.
The air is pushing him upward.
But gravity's still keeping him, pulling him closer to the earth.
You're skydiving. Do you go up in the air or you go down when you're skydiving?
Down.
You go down.
So he's
Or
moving
no.
down, then doing what?
But that at 2,900, the air force, the force from the air is
I guess it's
bigger.
still
It's bigger,
technically
so
falling.
so he's
I guess he's speeding up.
He's
Think about it. You just shot.
he's
Don't look at the
he's
numbers. Don't look at the numbers. Don't look at the numbers.
he's decelerating really fast, but he's still falling. At
Right,
the same
speeding
time.
up.
You think about logically. Why did you pull your parachute out? To do what?
Slow
So-
down and move
Because you're
down.
doing what? You're doing what in the air? You're doing what?
Falling.
Gliding.
Falling. You're falling in the air. So which way are you going?
You're always moving down.
Down. And you are going at a certain speed, but when you put the parachute, you want to do what? What is your objective?
Your rate of velocity has just changed.
Don't say no. This is
Or-
very simple. What are we trying to do when you pull the parachute out?
Stop.
Oh, stop or slow your fall.
So if you want to stop, you have to do what?
Slow down.
Slow down. So we're moving down and we're doing what?
Slowing
Speeding
down.
up. Moving
Think
down
about
and slowing down.
There we go. All right. Someone explain why the air resistance increases from 6,000 to 4,500. Just try your best.
Someone explains why the air resistance increases from.
Mhm.
So
Because-
as he begins to fall and stabilize himself, the air catches more and more of his body's surface area.
Okay.
I
Now, why
wasn't
the
gonna say
decrease?
it like that.
Go ahead. What were you about to say?
No, I was just gonna say because he's in different zones of the air and the air pressure is different.
I guess that is true.
Is it
Like the
someone?
altitude, like the altitude.
Okay, I see what you're going with right there. But I'll come back to that. Go ahead. What about the next one?
Explain why air resistance decreases from 3,000 feet to 1,500.
Yes.
Why it decreases. The
Air balloon is
the parachute stabilizes its form and it gets a more steady flow of air, and that makes it decrease into a normal state of terminal velocity. Is that it?
Let's see. Let's start from backwards with that last one, right? Air resistance depends on the cross-sectional area of an object, right? So with the parachute being open, and there's more cross-sectional area. Then we have to where the increased upward force exceeds the downward force and then slows the skydiver down, right? So once we get to a point, it actually slows down. We get to the air resistance, the cross-sectional area, to where now pretty much like it'll get to being now it slows down to where now the air resistance is actually equal to the gravity. So at first, we're getting to have the air resistance to be so much higher to where it slows down acceleration, but then we'll get to a point to where then the air resistance will slow the person down to where acceleration is equal to zero, and then we have it equal to now the force through gravity. So the goal is to have the air resistance be super high at first, and then it starts to decrease to where now it's like, oh, it's going to go ahead, slow this person down. Does that make sense?
Wait, say it again.
I'm still a little confused about 5. The skydiver is speeding up during this stage of the fall. The air resistance force depends upon speed. I
So
guess
now
that's
air resistance points because cross-sectional area is for like when you have the parachute, right? But now in this one, when the person is falling down and from 6,000 to 4,500 feet, right?
Mhm.
It depends on the speed as the speed increases. Like we do have acceleration due to gravity, right?
Mhm.
But because you're going down faster, now we're going to
okay, wait. Okay, yes. As you move faster due to gravity, the air resistance. Okay, I completely understand it. As you move
Yeah.
faster due to gravity, the air resistance increases.
And this is like when you coming right out the plane and you're starting to come and you're starting to get faster. You're gonna feel yourself like, oh, okay, I'm getting faster. And this will get to a point to where you're not gonna accelerate anymore, but you'll still be going at a high speed, right? But what you want out of that is that's why you pull the parachute out, because you're going at a high speed, but you want to slow down. So you literally need the parachute to create so much air resistance going upward to where now the acceleration, like we see, right? The acceleration goes from you going down to zero to now it's going upward to where it counteracts gravity to where now it's so high to where it's really starting to slow you down. Does that make sense? We good on that?
I'm good with that. Also, wouldn't surface area be a huge factor too?
Yeah, that's the cross-sectional area. Yes. Same thing.
Okay. All right.
Going upward, number 4, moving downward and slowing down. And then we see the two altitudes where we're speeding up. You can see at 6,000 and 5,500, because we see that acceleration is down, but it's where he's going, he's getting faster. And then 3,000 and 2,900, that's where we see where it's slowing down because we had the parachute being shot up, and we see the acceleration is going up. Pretty much the direction of this acceleration is going up for the bottom two, and then it's going down for the top two. That's what shows we're increasing versus decreasing, speeding up or slowing down. And then
There's more
terminal
cross
velocity,
sectional area. Okay.
4,500 and 1,500. All right. Now, that was a lot of math, but what does that bring us into? We're almost done, right? Sorry. That brings us into talking. That brings us into talking about this concept of the elephant in the feather, right? So suppose we have an elephant in the feather and they're dropped from a very tall building at the same height and same time. We want to say that we can just get rid of air resistance, right? So we're ignoring air resistance. We want to figure out what would happen with each of these animals, right? Or the objects. Let's just say objects, right? So we want to go through and do true or false for each one of the statements. So let's think about it, right? We're not talking about no air resistance, right? No air resistance. If there's no air resistance, right? The elephant and the feather will each have the same force due to gravity. Is that true or false?
True.
No, that's false. They have different
Same force
masses.
due to gravity.
I say true because they're both
Oh
falling
yeah,
towards Earth.
they both experience gravity the same way on Earth.
Force due to gravity. Gravity is a what?
A force.
Acceleration.
Acceleration. So the acceleration due to gravity is always what? Say it again.
9.8.
9.8. But the force due to gravity is also saying what? It's also the same weight as what?
Weight?
Weight. Now, do the elephant and the feather have the same weight?
No. Yeah. Okay. Then it's
Okay.
false.
There we go. I mean, I don't want to give you the answer.
They experience gravity in the same way that they
Yes,
experience
they
the
experience gravity,
9.8.
but you need to understand gravity is an acceleration. The force due to gravity is a force.
Gravity is the Newton's part.
So
Okay,
two
yes.
is true.
The elephant
Two-
has more mass, yet they both experience the same force of gravity. Force due to gravity is what? Say
It's the
other
same
word for it.
thing. It's what's
Force due to
acceleration?
gravity. Force due to gravity. Force
It's
of
the-
gravity.
It's the Newton's. So this one would be false too.
Okay. The elephant experiences a greater force of gravity, yet the elephant and the feather have the same mass.
False.
Okay, keep it going. On Earth, all objects, whether an elephant or a feather, have the same force of gravity.
False.
No. False.
There we go. The elephant weighs more than the feather, yet they have the same mass.
False.
False.
The elephant clearly has more mass than the feather, yet they each weigh the same.
False.
The elephant clearly has more mass than the feather, yet the amount of gravity force is the same for each.
False.
False.
Elephant has the greater acceleration, yet the amount of gravity is the same for each.
No, that's
True.
true.
Let's see how we did.
Oh, the
Victory, what
last
did you
false
say?
too?
Oh, they all false.
By amount of gravity, does it mean force of gravity or acceleration due to gravity?
They put it in the
Hmm.
parentheses, force. Yes, that's exactly what it is.
It's
amount
what?
of gravity. So
It's the
they're all
same thing
false.
as
Okay.
force.
Yes, it's the same thing as force. The amount of gravity is the same thing as force or
Force
Newton's.
of gravity is equal to weight. Force of gravity is equal to weight. And weight is based off your mass times the acceleration due to gravity. So it goes back to that play on to talking about mass and weight that we talked about earlier, but understanding that when it comes to now, how does that relate to force due to gravity and space? So this is without air resistance, right? Now let's do that same exercise, right? And let's think about it with air resistance. So the elephant encounters a smaller force of air resistance, therefore falls faster. True or false?
True.
Okay. Anybody else?
The elephant encounters a smaller force of air resistance and therefore falls faster. I think that is false. The elephant is bigger, has a bigger surface area, and so it would experience air resistance at a greater rate than the feather.
I hear true, I hear false. Anybody break the tie? Anybody to break the tie? True, false?
I say false as well, only for that same reason, elephants are like a lot bigger. So
They fall faster, but not because
All I
of the
needed is
force
another
of air.
false. Okay, go to the next one. The
The
elephant has
elephant
greater acceleration of gravity, therefore falls faster.
is accelerate.
I guess it's true.
Is acceleration of gravity equal to the amount of gravity?
Acceleration of gravity. What does it say?
It depends on the speed he's falling, and you know gravity is 9.8, so that means he's falling faster. They're basically saying that elephant is falling faster towards gravity.
Gravity is what you just said.
Force. Wait.
Acceleration, but you just said the number is what?
Newton.
I don't remember.
Say it again. What's the
Newton.
number for gravity?
Newtons.
Oh, 9.8. It's falling at
Oh,
9.8.
9.8.
9.8. So does the elephant have a greater acceleration of gravity than the feather?
No, false. They both have a 9.8 acceleration due to gravity.
That's the next
Wait,
one.
okay, let's go to the next one then.
Both the
Both
elephant and feather
That
have the
one's
same
true.
force of gravity, yet the acceleration of gravity is greatest for the elephant. Go to the next one.
Both the elephant and feather have same force of gravity, yet the feather experiences a greater air resistance. And I'm trying to think about a feather falling, and they fall so slow no matter how hard the wind is pushing. So I don't
But
know.
that's not due to
Victories in class saying false.
I think it's false because that's not due to the air resistance. That's more due to the mass of the feather.
All right, go to the next one. Each object experiences the same amount of air resistance, yet the elephant experiences the greatest force of gravity.
What
Each
is okay?
object
Wait.
experiences
This
the
one,
same amount of air resistance, yet the elephant experiences the greatest force of gravity.
and the force of gravity is
The push, the
9.8
resistance.
9.8 meters a second,
False.
right? Or what is so great force of gravity? Force of
Weight, force of gravity is weight.
is weight.
9.8 times its mass, not 9.8. 9.8 is acceleration due to gravity.
Okay, Okay, so the force of gravity is the weight. The
Elephant's
Um,
heavier than 9.8.
I think
So I
this
say
one
it's
is true.
false.
You saying true? You saying false? Victory, what are you saying? Victory said false, so I think we got to break the tie. Go to the next one.
Each object experiences the same amount of air resistance, yet the feather experiences the greatest force of gravity.
What is force of gravity?
Wait,
Weight.
Weight. It says the feather experiences the greatest weight.
No,
No.
that's false.
All right, go to the next one.
The feather weighs more and therefore will not accelerate as rapidly. That's false. As the
False.
elephant.
Both the
Already
elephant and feather weigh the same amount, yet the
False.
greater mass. Okay. The elephant experiences less air resistance and reaches a larger terminal velocity.
False.
Okay. The feather experiences more air resistance, thus reaches a smaller terminal velocity.
I don't even understand the question.
It experiences more air resistance. What gets more air resistance, the feather or the elephant?
I honestly don't know. Wait, how would you?
I put
Yep.
true for the first one, so it's between the. If you answer false for the first one, you have to answer true for this one. But I answered true, so I guess I'm gonna just put false.
Okay. The elephant and the feather incur the same amount of air resistance, yet the elephant has a greater terminal velocity.
That's false. And then for 10, I want to put true.
We got a false, and you said 10 for true. So really all of these we said false except for 10. That we going with?
I put true for 1 and 3.
The elephant and the feather encounter the same amount of air resistance. Yet
I
the
won't
elephant.
force you into an answer. I'll let you see for yourself how you did.
Oh, 1 is probably false. Well, they're
They're
all
all
false.
Yes. This was to break your preconceptions about how what you have about air resistance, and even just for based
That's
off
what I
of
was saying.
right? And for all of these too, we talked about the force, the force due to gravity. You got to be careful. We're talking about the force due to gravity versus gravity. Gravity is acceleration. The force due to gravity is the weight. And we see when we start talking about air resistance, how certain things change. I wouldn't say change up a little bit, but you got to be a little bit more careful when you're talking about two objects that have different masses, like an elephant and a feather.
I have a
Is the
question.
amount of gravity the
can you go
newtons
back?
or
Can you go back again? I don't understand the last three because which has more air resistance? Because if they're all false where it says which one has more air resistance? Is it the feather?
I understand her question. Like it's easy to think about the mass of a feather in a an elephant and be like, well, oh yes, this one's heavier, but then what
Which one has
about their
more air
properties
resistance?
gives
I
them
don't
air
understand
resistance?
that
Yeah.
one.
But it's three things that cause air resistance, right? You got speed, air density, and then cross-sectional area, right? So between which one would have more air resistance based off of not just, it wouldn't be their mass, it would actually be which one has more cross-sectional area.
The elephant. The elephant is experiencing
the-
more air resistance than
I thought the feather would have more cross-sectional area compared to its mass. So it would,
A feather compared to an elephant.
how much area does the elephant have? How much
yeah, I get
area does
that,
it?
but I don't.
Not relative. Don't think about relative to mass. Just think about area, period. How much wind is hitting the amount of area at any given time? The feather is only so big versus the elephant has many, many more, feet, inches, whatever you want to measure it as.
So
in
are we saying
space.
the air resistance, which area has more cross-sectional mass?
No, area. Because it's like how much, hold on. Give me a second.
How much area does it cover? How much space does it take up, basically?
Which one are you asking about?
The
Lakshmi?
last three, can you just like the not even the last three, the 9th and the 10th, I don't understand because
Yeah, I don't understand that one either.
I thought the sorry, is 9 true?
No, 9 is false. They're all false.
But you just said if they have more surface area, there's more air resistance. And 9 says it experiences less. Oh, wait.
The elephant has more surface area, so it would not experience less air
Oh, I see
resistance.
what you're saying. Okay. And then the feather experiences less.
The feather experiences less air resistance because it won't fall as fast due to its mass, and it doesn't have as much surface area as the elephant. I get it now. And those are the only three things, right? Speed, surface area, and
But
Air density.
how do we
air
know what
density.
speed is? Because they don't give the speed anywhere. So how do you know, like,
So then if you don't give the speed here, you would then, and we don't have the air density, what's the last one we could determine based off of?
Surface area.
Cross-sectional area. So that's what we use to determine this. They didn't give us
So
a
it's
speed.
speed,
I don't know if you're guessing this.
air resistance, and what? I'm sorry.
Speed, air
Air
density,
density.
and cross-sectional area.
So speed, air resistance, and cross-sectional?
Air
Air
density,
density. Air
Oh,
density.
air density, sorry. Thank you.
cross-sectional area.
okay, thank you.
We good?
This is making so much sense.
All right,
I just don't like air resistance.
I can see. All right, we are almost done, right? Now, this gets us now, we didn't cover a lot of first and second law stuff, right? But what I said earlier about forces and how they come in pairs, right? So we have action and reaction forces, right? So this starts us to get to understanding, like I said, forces come in pairs. So an action force is the initial force exerted on the object, right? Then we have the reaction force, which is the equal force exerted on the first object, but in the opposite direction. Now, that might sound confusing, right? But let's go ahead and play around with it, right? So this starts to get us to understanding action forces, is the initial force exerted object. We have the reaction force, which is the equal force exerted on the first object, but in the opposite direction, right? Now, how does Newton's Third law bring all this together? For every action, there's an equal and opposite action. What does that really mean, right? Let's look at this problem, right? So if we can say that forces come in pairs, right? We can describe motion in a pair type of way, right? So let me do the first one, right? So let's say the athlete throws the medicine ball, right? That's just the what we see, the verbiage, right? The verb is throw, right? Or let's say push. Let's say athlete pushes medicine ball, right? What would be the opposite, the equal but opposite reaction force? Athlete pushes medicine ball.
The ball goes flying in the opposite direction, or hit him back in his face.
Yes. Okay. I see where you're going with it. Now let's just use the same 3 words that I said. Athlete pushes medicine ball, or 4 words. How would I do equal and opposite?
The ball would
Would
hit him
that
in
be
his
like
face.
normal force apply here or no?
It's actually really simple. Y'all just gotta just flip the words around. Athlete pushes medicine ball. What's
The
equal? and
ball
opposite?
jumps in the athlete's hand. The ball
The
is
ball
thrown in his
pushes.
hand.
The ball pushes back at the same time he's throwing it.
Just use the same words and just flip the direction.
The ball
Athlete
is
Medicine
in,
ball.
medicine ball.
Medicine ball pushes athlete.
Exactly.
That's
Do
what
the
I'm
same
saying.
thing.
As a ball leaves your hand, the ball is also putting a force back on you.
Yes. 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 Say the next one.
Foot touching floor, floor touching foot,
Verb. You need a verb.
or a foot
It's a push or a pull because it's a force.
it's a
foot
push.
push. I think they're stepping up.
The
foot
floor
push.
comes up though. The floor could, because of
Push.
gravity.
What's the first one? Foot.
Foot pushes against floor. Floor
Okay.
pushes against foot.
There we
Right.
go. Next one.
Foot kicks ball. Ball kicks foot. The foot pushes backward or down on the floor. The
All
floor
we added was a
pushes
direction. We said
That's
foot
what I was
pushes
saying.
floor.
The floor pushes up.
That's fine. You said floor pushes up, so that means the foot pushes down.
down.
Same thing. Foot pushes ball forward, so then the ball pushes the foot which way?
Backwards.
There we go. Now, how does this come all together, right? Let's look at Newton's third law in conjunction with Newton's second law. So we even had the first law, we said the sum of the forces equal to 0 unless all the forces are equal, unless it's enacted by an unbalanced force, right? So when it's acted by an unbalanced force, we get to Newton's second law, right? Which means that the sum of the forces equal to mass times acceleration. And then because we know now Newton's third law, we know that when we see forces being present, they come in pairs, right? So let's look at this first one, right? A bullet is loaded into a rifle and a trigger is pulled. The force experienced by the bullet is less than, equal to, greater than the force experienced by the rifle.
Equal
Think
to.
about it. Equal to, right? So now we know that it's equal to, but the resultant acceleration of the bullet is less than, equal, or greater than the resultant acceleration of the rifle.
Greater than.
Okay. Why do you say greater than?
Because the bullet goes out at such a fast speed.
Because of why? Why? What's different between the
Acceleration.
bullet and the rifle? The acceleration is different, but what else is different?
The mass.
Velocity.
The mass.
Oh, the mass.
Think about it. If they have the same quantity of force, right, the same equal force, that has to be different between them is their mass, because now we have different acceleration. The mass is what determines that acceleration. Well, I'm not gonna say the mass determines acceleration. The force is the force, right? But if the mass is different, right? One has a smaller mass, that means it's gonna have a high acceleration. The one with the heavier mass is gonna have a slower acceleration. So let's think about the next one. Tell me about the next one. A bug crashes to a high-speed bus. The force experienced by the bug is what? Less than, equal to, or greater than the force experienced by the bus?
Less than.
Go back to third law.
Oh, no, I'm sorry. It's greater than. It's greater than.
Go back to third law.
What? For
Every
every.
force-
Oh, it's equal. It's equal because for every action, there's an opposite reaction.
Yes.
Opposite or equal.
Opposite and equal, right? But now
Yeah.
the resulting acceleration of the bug is less than, equal to, or greater than the resulting acceleration of the bus.
Equal to.
It's less than. The acceleration of the bug is less than.
I said less than. I don't think it was right.
Go back
And
one
the
more
f-
time. The force experienced by the bug is less
Is
than,
equal.
to, or greater than. The
Or
force
it's equal to.
So
the
the
force
forces are
is-
equal, right? Now,
Right.
But the acceleration is less than.
the acceleration of the bug.
It's greater than because it's flying at the bus. It's crashing into the bus at a rapid
And the
What's
bus
difference
is moving.
between
The
the
bus
bus-
is moving. The bus is moving too towards it.
But what's the difference between the bug and the bus?
The mass, because the smaller the mass, the
The le-
greater the acceleration.
There we go. We're starting to get it. Okay. A massive linebacker collides with a smaller halfback at midfield. The force experienced by the linebacker is less than, equal to, or greater than the force experienced by the halfback.
equal to.
Equal to, right? Now the resulting acceleration of the linebacker who is massive, is less than, equal to, or greater than the resulting acceleration of the halfback. There we
the
go.
acceleration of the linebacker is
Victory
Greater
came
than?
off because it's less than.
greater than.
The linebacker is massive. So the linebacker's acceleration is going to be what?
Oh, less than. He's gonna
There we
move
go.
slower because he's heavier. Oh,
All right, now this one, pay attention. This is supposed to trick you up, right? The 10 ball collides with the 14 ball on the billiards table. Assume equal mass balls, right? They all the balls weigh the same. Sorry, not weigh the same. They have the same mass. The force experienced by the 10 ball is less than, equal to, or greater to the force experienced by the 14 ball.
Equal.
Equal, right? Now, think about it. The resulting acceleration of the 10 ball is less than, equal to, or greater to the resulting acceleration of the 14 ball.
Greater.
the
Or
resulting-
wait. It's equal to as well.
Why'd you say equal?
because you said they're all the same.
Same what?
Mass.
How we do?
Wait. Equal to, greater than, equal to, greater than.
So it's equal to, greater than.
So something smaller has a greater acceleration, but is that, are we just assuming that? Like a high speed
How are you
bus,
assuming that? Think
a
about it. We
high-speed-
just talked about two laws, right? We have Newton's
Mhm.
second law and Newton's third law. The sum of the forces when it's unbalanced is equal to what?
is equal to not zero?
Oh, it's because acceleration is force divided by mass, and mass is in the denominator. So the bigger the denominator, the smaller the result will be.
Yes, if you switch to the formula around, you do have acceleration is equal to force divided by mass. That's typically how physicists talk about it, to be honest with you. The acceleration is caused by force over the mass, yes. But so that's really it. As the mass increases, the acceleration is equal to force over the mass. So as mass increases, it will make
Acceleration decreases?
yes.
But how can a high speed bus have less acceleration than a bug? A bug can't go as fast
Because
as a bus.
because the bus is faster. I mean, because the bus is bigger in mass. So it's
So the
it takes-
force that the bus feels from the bug, though, right? Like the bug
Mhm.
hitting it,
It's
think about
equal. I get that part. Yeah.
it's equal, but like, is it going to be, because it has so much mass, acceleration is going to be so small, right? Now think about the bug, right? The bug is going to feel that acceleration because it's so small. It's going to have a really high acceleration. What in turn, think about what logically happens, right? What happens when the bug hits the bus?
It gets squished. What are you talking about?
Yeah, it gets squished because it feels that high
speed.
or
Acceleration.
The acceleration?
yeah. So that's a force, right? When we talk about later on. You talk
Oh,
about,
okay. I get it. So it's the experience of the acceleration at the moment, not just them accelerating, period. Because I was like, well,
It's
a
the
bus
speed
is
too.
A
Even
bus
think
can
about,
accelerate.
the bullet, right? Think about the bullet, right?
Mhm.
The bullet is coming so fast, but it's very small. But it's also like it's coming all that force because now think about what a bullet it comes in. If it hits you, it's gonna pierce through your body because it's all that force. But it's
Mhm.
coming at a high. It's a small, massive, small object with mass coming at a very high acceleration.
So are we talking about the acceleration of the bug after it hits the windshield?
Like the impact. Let's say like right at the impact.
Okay.
Does this
Was
make
Okay.
sense?
Why am I? Wait, I'm not getting this. I get it for the bullet. Like I get why because the bullet is simply going faster.
It's
The
literally the
bullet
same thing.
is simply going. But how is a bug going? Accelerating and going faster than a bus? What bug goes faster than a high speed bus? That's what I'm saying.
The resulting acceleration from the bug crashing into the bus.
Meaning, the greater acceleration is due to the bus.
Are we talking about like negative acceleration, like the opposite direction? That's why it's greater, or?
When it hits the bus, the acceleration that it feels.
It goes flat and then it goes in the opposite direction. That's the acceleration. Like I
Like a
mean,
bus
but
is running is going high speed and the bug is going whatever direction and it feels that, right? It's going to feel a greater acceleration than the bus is going to feel from the bug hitting the bus. That's what it's saying. The acceleration due to the bug hitting the bus is going to be greater than the acceleration of the bus hitting the bug.
okay, that makes more sense. I thought it was saying, acceleration period. Like, if these two things were coming head on, which one had the greater acceleration? And I'd be like, well, the high speed bus would have a greater acceleration than a
Yeah, that's
bug.
what I think too. But like the only reason I selected the right answer was because of the formula. I just blindly followed the formula, and
But
that
don't
makes
blindly
sense.
follow the formula. Think about it actually for what it is. You
But
got two
like, it
massive.
doesn't make sense if you think about it for what it is. How can a bug have less or more acceleration? It makes no sense to me.
Because again, it's conceptual, and we're talking about at the when these two forces meet. Let's say they're going in opposite, or no, this wait,
The
how does
force
that
that
work?
the bug
They're
feels.
going into
bus is going-
perpendicular directions.
No, I
the
would just
bus is
say if you
going-
make a, sorry, go ahead.
The bus is going at a very high. The bus is traveling, right? And that's a very high force, especially when it makes the impact, right? To replicate that same equal and opposite force, it has to be a high acceleration because the bug is not as massive. The bus is going to produce that high force by hitting the bus. Yes, the bug,
Yes.
right? But for that bug, what it feels is going to have that high acceleration because it does not have as much mass as the bus.
The bug is being overtaken by the bus. That's why the
And the force is
resulting
acting on the bug. Bus hits bug.
and the resulting acceleration from the hit is the resulting acceleration of the bug from the hit is greater than the resulting acceleration of the
Are we
Um,
mixing up speed and acceleration?
No. Acceleration.
No,
Because I feel like maybe that's why. Because they're going at different speeds, right? Like the bus is going faster.
but it
Obviously.
says a high speed bus. So like what is
Yeah, so
there's
the
no
bus is going faster than the bug, but yet the acceleration of the bug is higher than the bus.
The acceleration that it feels as a result due to the
of the
force.
So like
crash.
the bug's speed, we're just talking about how much the bug's speed changes, not the speed itself. Is that right? Like it changes like really drastically compared to the bus's speed because the bus just keeps moving. It doesn't really feel the bug.
And
the
that's the
bug
greater than part.
is the bus. So like
That's
relative.
the greater than part, yes. So the force that they feel is the same, but that acceleration is not going to be the same because the bus is more massive. So
And it's
therefore,
going to cause the bug to accelerate at a greater rate than the bus is
forces
causing the
have to
bug
be
to
equal.
accelerate at a greater rate
Like
than
if you
the
say the bug was going at like, I don't know, 5
5
miles
miles.
an hour. So like its acceleration would change would be really high, and so change to like its speed would change to 0. Like
Oh, now I get it from that point. Now I get it from the formula point. Ooh, that makes sense.
is that what we're saying? Like it's a really huge acceleration, but by acceleration we mean deceleration for the bug, I mean.
I'm just saying in general that the acceleration is going to be very high because the acceleration is high because the mass is very low. Like just simply like the having the mass, like the force has to be the same. The difference between them, those two objects, is their mass. So if the mass is heavier in one, then that means acceleration has to go down. It's just like literally just looking at like sliders on like a graph. Like literally, that has to go like one goes up, the other one has to go down. That's what you have to think about logic like that. They have the same force, but what difference in their quantities is the mass and the acceleration. And we know what their masses are, so therefore their acceleration is going to fluctuate. Their mass is always going to be constant.
Right. Okay.
So as a review, right, we have Newton's laws, right? So the first one, we have an object at rest will stay at rest, and an object in motion will stay in motion when acted upon an unbalanced force. Newton's second law, when forces are imbalanced, and that force is equal to the mass of the object times acceleration of the object. And then the third law, we have for every action, there is an equal and opposite reaction. So when we get back here tomorrow, right? Oh, not tomorrow, on Wednesday. Have a good night. We'll go ahead and we'll go through the second law problems, and I believe that leads us into talking about, let me just see real quick. Yeah, our last two. So I'll do pretty much a recap. I'll bring us into our second law problems, and then we'll kind of go right into finishing up, and then I'll transition us somewhat into the next unit, which will be unit 3. So I'll try and do all that next class, but this was a lot. Thank you for being patient with me. And I think we should be good to where our next class will be virtual, and I think I'll start at 7, but I'll make sure I send a reminder. So plan to start next class at 7, unless I tell you otherwise.
Question. Is there like practice exam or anything after the second unit?
So the next practice exam is going to be after the 4th unit. So it's going to be 2nd, 3rd, 4th, and then practice exam.
Okay. Okay.
All right.
Do you have any problems you can give us? Like, just put it on Blackboard, any extra ones by chance?
Just do the practice problems. Literally the practice problems. Like the whole practice problem.
It's the packet. Yeah, we've been following the packet.
Yeah. Like,
Because I don't
actually
think that
sit down-
you covered every single problem, right? There's
No.
No,
There's
I'm
still-
only doing one problem for each section. Like, I want you to go through and do the practice problems, like, on your own, even what you have in the answers, like sitting down and doing them, because they all repeat each other. Like, I only pick one because, like, they're literally going to repeat each other. So it's like the repetition. Once you, like, see how one works, that's why I explain it once, so that you can go practice it. So then you'll be like, oh, this is similar to the other one. Yes, they're actually meant to do that. So that by the time you finish the practice problems, you'll be like, oh, I've done this type of problem like 3, 4, 5 times. Does that make sense?
That makes sense.
Okay. All right. Get some rest, guys. Thank you for being with me tonight. This was a long class. We're almost done with this unit, so we'll be done next class Wednesday. We'll start at 7, but everyone have a good night. I'll stay back if anybody has questions.
Okay. Thank you.